Welcome to one of my favorite topics, exploring quality issues with statistical tools. Ross says there's 4 uses of statistical tests, but I beg to differ a little bit on the table that he presents. He says we can identify problems, that's true. Analysis of means, chi-square, and ANOVA are all good tools for that. We can identify the causes of problems using regression analysis, but I say no. We can identify an association, possible precursors, but we cannot really identify the causes. We can identify potential solutions and select a solution, but I would say what we really want to do is select a solution to test, to see if whatever we have done, perhaps an intervention or change the process somehow, has made a difference, a statistically significant difference in the outcome. And of course we can monitor change using chi-squares and ANOVAs. So lots of great tools, but as I said, we want to use the correct terminology in this, and we are not identifying causes necessarily. So using these tools in quality management is a little bit different than research, but certainly there is an overlap. They're not mutually exclusive. In research, we're doing basic testing to expand our knowledge, and quite often we try to use a randomized controlled sample of some sort so that we can generalize to a larger population. Quality management utilizes the same tools quite often, but we're not going to be able to generalize to a larger population. We'll just be able to look at the population within the institution or the sample that we're testing. But they are great tools to help us identify whether the changes that we've implemented have actually made a difference. Is it a significant difference? The first tool we're going to look at is chi-square analysis, which is a great tool for looking at whether there's a relationship between two categorical variables. So it looks at problems, potential causes, and whether interventions were effective. And the formula is simply chi-squared is the sum of the observations minus the expected observations divided by the expected observations. And you'll see what we mean by that when we look at an example. Here's an example where a hospital has instituted a hand-washing program, and we want to know that was there a difference between the number of infections noted from before they instituted the program to after. And what the computer program does in chi-square analysis is based on the proportions that we see here, so pre-implementation versus post, and these are the observed infections. We have 14 versus 8, and out of 259 over here and 294. The computer generates then what they think, what the expected would be based on the proportion, and the expected is 10.45. Post-implementation, 11.55. So as you look at this, you think, well, there is a difference between 8. We've gone down, yay. But was it really a significant difference? And when the computer spits out the results, the p-value is 0.1217. And if you think back to statistics, you remember that we really want it to be less than 0.05. We don't want it to be greater than that. So in the hand washing example, it's not statistically significant. The chances are that it didn't fall outside of this normal curve. If you remember back to stats, that if it falls, we're looking at what are the chances that it's in these tails and not under the normal curve. And the p-value that is less than 0.05 says it's within the normal curve. So there's really not a big difference. We didn't by chance. Here's another example from my own research with a colleague where we looked at charts from a year's worth of admits to an inpatient psych facility, and we were looking at the presence of sibling violence, so any kind of verbal or physical abuse between siblings. And we wanted to look at gender differences, and so we used chi-square since we were looking at two categorical variables. And we wanted to know, was there a difference between boys and girls? And what this showed was that for this particular type of violence, hitting, kicking, pushing, shoving, that boys were much more likely to use this than girls. And if you look down here, 0 is a no, and 1 is yes, it's present. And you can see this is from SPSS and how it spits out the results. And so this is the actual count of boys and the expected count. So the computer's saying I really would have expected to see 61.5 boys use this, but there was more. And for girls, we would have expected to see more actually. And so we have a value then of 0.021 for the p-value, which is quite a bit below 0.05. So there is a significant difference between boys and girls on this particular variable, which wasn't surprising for us. And the critical value, 5.29, that's a pretty big value, so that just tells you that there's going to most likely be a statistically significant difference. Doing an analysis of variance is really handy if you want to determine if there's a significant relationship between a categorical variable, typically the independent variable, and a continuous variable. For example, you might want to look at types of people, as we just talked about, perhaps boys and girls and so forth, or patients, physicians, and does that group have significantly different outcomes in measures such as length of stay, which is a more continuous variable, or some outcome variable like blood pressure, A1C levels, and so forth. So the equation is that X is the independent variable representing the data from the whole sample. U is the overall mean, so we're comparing against the overall mean, and T is the difference between the group mean and the overall mean plus the overall mean. Oh, and E, sorry, is the unexplained variance. When you start getting into things like analysis of variance and regression analysis, you always have some variance that's unexplained. So we're always just explaining part of what is causing whatever the outcome is. So I thought this was a great example of an analysis of variance problem where we want to look at pain levels in patients, and we had some patients receive some education as an intervention on how to perhaps control their pain, and then how does that compare with the group who did not receive the intervention? And it's interesting, if you look at the means here, you can see that the control group and the patient group are very, very close. So I would imagine the answer might be that they are not significantly different. Now what's interesting with these results is that, as you can see, the p-value is below 0.05 and the critical value is less than 3.63, which tells you that yes, you're going to have a difference. But because we've got 4 groups in here, we know there's a difference between 2 groups, at least, but we don't really know which groups. Now if we look at the averages, we can see that the staff and the patient gauge for pain is quite different than the control group, and also the patient group. So we might want to go back and run additional tests for just 2 of the groups to nail down exactly where that variation is. Because it's interesting that the staff and the patient observations are so much lower than everyone else. It makes you wonder what other variable is at work here that that rating would be so much lower. Because I would guess that these, particularly the control and the patient group, are very similar. 5.9 is not much different than the others. So it warrants further testing. The other test you might do for this, if it's just two groups, is a t-test, which is basically uses the same mathematical approach, but it's just for two tests. And if it's the same group, with the same group of patients that are tested before they get the educational intervention, and then after, you can use a paired t-test, which would give you some good information. But this makes me wonder about what's going on with the staff ratings. An analysis of means is kind of an interesting approach to testing differences between groups. It looks at whether the individual or the group performance is significantly different from the average. And it sort of combines an analysis of means, looking at differences between, the central tendency line, but also it reminds me of the P-charts that we did a couple of chapters ago, where you come up with a control chart that varies according to the sample size. So we'll see a good example of that in a minute here. This is a great example of using an analysis of means where we're looking at physicians' prescription rate of Ritalin and trying to decide, is it too high compared to their colleagues? Now, of course, I don't have to tell you what's wrong with this we should also be asking, is it too high compared to standard of practice established by some good benchmarks? But we're just looking at our own physicians and comparing their prescriptive patterns, and it looks like, of course, physician number 8 is much higher than the rest. But then we look at his the number of patients that he sees or she sees, and the percent is actually not too far out of whack compared to number 3. So we can already see that number 3 is probably going to be the outlier in all this, just looking at the percent or the proportion, similar to what we did with the P-charts. So here's the output for the analysis of means, and as a part of that, we compute an upper and lower control limit, right here, and the mean, this is the grand mean for the central line that's going across right here. And as we thought, physician number 3 is actually outside of his or her own upper control limit. So that person is just going crazy prescribing that Ritalin. Whereas physician number 8 that we thought might be quite high is actually pretty much in the pack down here, interestingly. So it's a great tool when you're looking at a sample size that really differs, or you could just do a P-chart for this as well. Very similar results, and it'd be interesting to compare those results. Regression analysis is a great tool that looks at the relationship between two continuous variables. So if you have data that's not categorical, it's a great tool to use. Now there is something called logistical regression analysis, which you can use with categorical variables. So if you have one variable that's categorical and another one that's continuous, you can use logistical analysis. We're looking at regression analysis, so it not only determines the statistical significance, but it also looks at the expected change in the dependent variable given a change in an independent variable. And I know you all will recognize this as a piece of scatter charts, which we've done before. So the equation for this is really important to understand, and that y is the dependent variable. So it's a variable we're predicting what's going to happen. A is the intercept of that line, so somewhere on this y axis. B is the slope of the line. So depending upon the line that goes through the data, so is the slope steep or not so steep? And then E is always that unexplained variance that we just have with every equation. So we're never going to capture 100% of the variance in a statistical equation. So here's a scatter plot diagram that we've done something similar before, and there definitely looks like there is a relationship here between the average charge and the case volume. And frankly, I thought this was not a very good example from the book, because we kind of peek up here, and it almost makes you wonder if as we get higher in cases, if there isn't some economy of scale as we get down in this range, right? Of course our costs are going to go up a little bit, but per case, when you think about it, they really shouldn't go up that much. So I think this is kind of a crazy example, and that we have an outlier up here, but this is the example that Ross used. So in looking at the output from this regression analysis, there's a few values that we want to hone in on. One is the adjusted R-square, which tells us how much of that variance is explained by the volume. So how much of the charges are explained by the volume, and 30%, so that's quite a high percentage. 30% is good. It's a moderate, in terms of how much is explained, it's a moderate value right there in the middle. And then we want to look at the t-stat down here and the p-value, which is less than this, so it's significant. It's very significant. That's written a little bit differently than we normally see p-values, but trust me, it's good. So a significant amount of change in price is explained by that variable, by the volume. And for every case, interestingly, the price goes up $13.10. And then this is the y-intercept, so at 0 cases, this is how much we're charging, I'm sure, for that particular procedure. But I would still look at this a little more closely to see perhaps doing a cost-benefit analysis, or perhaps a break-even analysis to see what's going on with the charging, because we know this is a significant variable, but are we really achieving the efficiencies that we need to be achieving is what I'm wondering. As volume goes up, prices should go down, or perhaps should be more in a step fashion. As you get to so many cases, you have to add so many fixed costs, and then you're able to get some economy of scale in there. So, as always, it raises more questions than answers. We can also use something called multiple regression analysis if we have a number of variables that we want to examine in terms of what their impact is on the dependent variable, such as perhaps weight, exercise, and diet, on cholesterol, which is very, very handy. And what I like to do, if I have a complex equation, is I like to use something called stepwise regression. So I enter like variables one step at a time to see what the cumulative effect is of the variables, because as we know, particularly with human behavior, what explains the dependent variable can be quite complex. So for example, you might enter demographic variables as one block, then socioeconomic sorts of variables as another block. That's what SES means. And then a variable of interest such as depression, when we're looking at outcomes. So that can be a very, very handy approach if you're looking at something a little bit more complex. So in summary, remember that Small samples of convenience can't be generalized to a greater population, but certainly you might be able to generalize that to your own system that you're testing. And the whole point of quality improvement sometimes is to just gauge, where are we now? We've made these changes. What's happened to our system? Are we making improvements, and are they significant? Because some of these improvements are costly, so it's nice to be able to do some quick testing and see if you're really making a difference. Remember that you cannot predict a specific outcome for one patient based on a larger sample, no matter how big your sample is. So I never want to hear anybody say that if you do this, thus and such will happen, because all we can really say is that there's an association between those variables. There's a strong association between those variables. If you take this medication, very likely it will help you. But as we know, people and diseases are very complex, and you cannot predict specifically what will happen with a certain individual, even though we might have overwhelming evidence that actions or medications or whatever will have a certain result. If you want to make predictions, you need to conduct research across time. Very important, not cross-sectional data. I can't tell you how often I hear people say that one variable predicts another. Even very educated PhD type folks will say that using cross-sectional data. All we can say is there's a correlation or an association. And that's very important information. I don't mean to discount it. Those are very informative bits of information that we can use to formulate interventions or changes in systems. But in order to do predictive research, it really needs to be across time.